Hey everybody, my name is Scott, and today we're going to solve the find leaves of binary tree problem on LeetCode. The problem definition is pretty straightforward. We're given a binary tree. We need to collect the tree's nodes as if we were doing this action. We were collecting and removing all the leaves, and then we repeat until the tree is empty. So that's not the most intuitive thing ever, but take a look at this tree here. So here's the initial tree, here are the initial leaves, 4, 5, and 3. So the first element we return is 4, 5, and 3, first element in the list. Now, visualize once these are gone, 4, 5, and 3 are gone, what are the leaf nodes? 2 would be the only leaf node. 2 has no children at that point, 4 and 5 are gone. 3 is gone, 1's not a leaf node because 2 is still its left child. 2 is the only leaf node, so we remove 2 in that step. 2 becomes the next element we return. And then 1 is the only node left, making it a leaf. It has no children, and that's the last one we return. There's a little bit of a explanation here. Here's what it looks like after removing 4, 5, and 3. So 2 is the only leaf left. We remove 2. 1 is the only node left, making it a leaf. And then we're left with an empty tree. And we return 4, 5, 3, 2, 1. This problem is kind of interesting. It takes a little bit of thought as to how these are being gathered up. And I was thinking about different tree traversal algorithms. The one I kept coming back to was level order traversal, which seemed to make sense to me. And using level order traversal, there may be some way you could rework it to where it works, but eventually the way to solve this problem is thinking about the height of each node. Now the height of a node in a binary tree is the number of edges from that node to the deepest leaf. For instance, 1 here has a height of 2. 1, 2 to 5, or 1, 2 to 4. 2 has a height of 1, 1 to 5, or 1 to 4. And then 1 does not have a height of 1 because it's to the deepest leaf. This is not the deepest leaf, it's 4 or 5 down here. 4, 5, and 3 all have heights of 0. No edges to any others, they are leaves. So when we start classifying these things by their height, classify each node by its height, then we realize that is how these things are being gathered up. We gather up all the leaves, we gather up all the nodes at height with height 0. We then gather up all the nodes of height 1, and then all the nodes of height 2. And that's the intuition behind the algorithm. So let's implement it. So I'm going to keep a hash map, because hash maps pretty much always come in to save the day. The keys will be integers. The values will be lists of integers. I'm going to call it heights. Also going to keep track of, and I need to move this guy up top, make him a global variable. Also going to need to keep track of the maximum height. And the reason I'm doing this is because at the end, when we loop through and gather up all these sets of leaves, I want to know what keys are actually in the hash map. That's just keeping track of the keys in the hash map. Alright, so all we're going to do in our function, we're going to call height from the root. We'll write the function height here in a minute. Bump this guy over 1. And then the list that we will return is going to be a list of integers. It's just all the leaves in their appropriate order. Call it toReturn. Now what we're going to do here is going to loop from I up to and equal to the max height. And why are we doing this? This is because for each height from 0 up to the maximum height of the tree, there will be a key in this map that has the nodes that are at that height. We're going to add whatever is stored in the map there. And then finally we will return that. That doesn't do any interesting work though. Let's write the height function. I'm taking a tree node, call it root. Alright, so this will be a recursive function. We got to bottom out the recursion. So if root is null, what if the root is null? Well, what is the height of a null element? Well, it could be 0. We'll just define it as -1. Doesn't really matter, it's just a way of bottoming out our recursion. Now, if it's not null, we're going to calculate the height recursively. And the height of a node is equal to the maximum of the height of the left subtree and the height of the right subtree plus 1. So this is definitely something useful to take note if you haven't seen it before. Here's basically how you calculate the height of a node in a tree. It's the maximum height of its left subtree and its right subtree plus 1. Why the plus 1? Because that is the edge that it takes to get from the left child or the right child up to the current node. Now if heights has the key of height, remember the heights are storing all the nodes at that height. We're going to get that list and add the root's value in there. Does not, then we'll set up a new list of integer, call it nodes, nodes at that height. And we're just going to add the root in there and then place it into the map. And we are keeping track of this max height, so let's do that. If the height that we found is greater than our max height, then the max height becomes height. And then finally we're returning an integer, we'll return the height. That should be that. Let's see what the compiler says. No suitable method. Add a tree node. Let's take a look. Of course, this should be root.val. We are storing the values stored at the node, not the node itself. Looks pretty good. Let's submit it. Internet being predictably fast as usual. Alright, accepted solution. So, heights of binary trees. Just remember, when you're faced with a binary tree problem and you've got to do something concerning the nodes, for me it's easy to think about in order, post order, pre-order, depth first search, breadth first search, level order traversal, all these different tree traversal algorithms. Don't forget the height and the depth as well. Those can always come in handy. And should you decide you need to calculate the height of some node in a binary tree, this is how you do it. The height of a node in a binary tree is the maximum of the height of its left, the height of its right, plus 1. That's all there is to it. We'll see you next time.